Okay, let's continue where we left. The other day we were having a look to using message passing with graph neural networks for simulating discrete systems of particles. So we'll begin by summarizing or looking back to some of the things that we had a look the other day. So we had a look to the concept or the idea of message passing. We have three steps for message passing: the edge update, the edge aggregation, and then we have the node update. So in the edge update, we apply it to each of the edges, and we take the features of the edge, the features of the sender node, and the features of the receiver node, and we feed them to an edge update function, which can be an MLP. For instance, here we are taking the features of the edge as a vector and concatenate it with the features of the sender node and the features of the receiver node. And this goes through a layer normalization and then the MLP, and we can have a weighted skip connection. Then we have the edge aggregation, where for each of the nodes, well, this step here, the edge update function, we apply it in parallel to all the edges. So for that, we can use the batch dimension of the MLP. Then we have the edge aggregation. For each node, we consider its neighbors, and we compute or we apply some permutation invariant function, generally the summation or the mean of those messages. And then we have the node update function, where we take this aggregated value together with the current values for the node features. This goes through the node update function, which again can be an MLP, so we just take the features, the aggregated features for the edges and the features for the central node, concatenate them into a single vector, and then this goes through a layer normalization, MLP, and we can add a weighted skip connection. So this was summarized in this algorithm with these three steps. And we also saw first an alternative where instead of updating the value of the edges, we are just computing a message, using that message for doing the aggregation and then updating the features of the nodes. But the next time we evaluate a message passing function, the features of the edges will be the same ones that we had at the beginning. We are not updating them. So this will be faster to train because the backpropagation chain is smaller, but also the accuracy can be a bit lower. And last day we started having a look to this paper by DeepMind titled Interaction Networks for Learning About Objects, Relations, and Physics. It's one or the first paper looking into GNNs for simulating physics, because it's the first use of it. They look into simple systems. These are discrete systems with only a small number of nodes. So during training they use 6 nodes, I think, and then at inference time they can use a larger number of nodes. They use up to 12 nodes. And the 3 problems that they consider were the n-body problem, balls bouncing within a box, and a string interacting with a ball. We saw at the end of the last lecture that this simple or relatively simple physics can be explained using our message passing framework. So just with one single message passing layer, we can represent the dynamics happening in the n-body problem. For instance, we saw that in this case, the message will correspond to Newton's gravitational law. The aggregation, which in this case is the summation, corresponds to the sum of forces, and then the Euler integration for updating the location of the nodes corresponds to the node update. Okay, now we can have a look to the different inputs and representations that they use for each of these problems. So let's begin with the n-body problem. We have n nodes, one for each of the bodies that we have, and in this case each of the nodes is receiving some attraction from every other node. So when we create edges, we need to create an edge connecting each node with every other node. That's why we have this number of edges, and we have a -1 because we don't have self loops. The inputs for each of the nodes are going to be the velocity and the mass, And for each of these edges that we have created, the input is the relative position. This is, well, a two-dimensional vector because we are in 2D. And here is important to notice that as input we are not providing here the location of each of the nodes. We don't want that, because if we do so, then this model will not be translation invariant. If we shift the system of coordinates, or if our bodies move to another area, the inputs will be different, even though the underlying physics should be the same. So with this, we only have differences or relative positions and derivatives of those positions, in this case the velocity. So since all the inputs are invariant to the location of the system of coordinates, then the graph neural network is also going to be translation invariant. And for training, they consider 6 nodes. Then the other problem was the balls bouncing within a box. So in this case, we have two types of nodes. First, we have nodes for the balls, so these balls moving here, and these balls can also collide with the surrounding walls. So in order to provide information about this, these are discretized also into some cells, and each of these cells is assigned another node. So we have ball nodes and wall type nodes. And similar as before, they create edges connecting each node to every other node. In this kind of problem, it would not be needed to create so many edges. We could simply connect each node to the closest nodes, or the nodes within some sphere of radius r. But well, in this paper, because it's one of the first ones, they use a complete graph or fully connected graph, following the nomenclature that we introduced at the beginning of the last lecture. For each of the inputs, for each of the nodes, the inputs are going to be the velocity, the inverse of the mass, the radius of the ball, and the node type. So here you may be wondering, why are we using the inverse of the mass instead of directly the mass? That's because we understand the mass as the resistance to having some acceleration when we have a force. So in the case following that definition, for the nodes located on the wall, the mass will be equal to infinity, and because we cannot provide an infinite value as an input to the network, we work with the inverse of the mass, so these nodes will have a value equal to 0 for this attribute. And regarding the node type, in this case we only have two types of nodes, ball or wall. So we could simply use a mask with the value of 1 for the ball type nodes, and a value of 0 for the wall type nodes. And the other problem was the string interacting with this ball. So in this case, the number so in this case we have nodes discretizing the string, and we have another node for the central ball. And the edges are going to be created as follows. So we have edges connecting adjacent nodes in the string, along the string, and then we also have nodes connecting each of these nodes to the central ball. So it will be edges like these ones. So in summary, the number of edges that we have is this. The first term here corresponds to edges between nodes in the spring, and here we have edges between here we have edges between the nodes in the spring and the central node. And the inputs are similar as before. We have the velocity, the inverse of the mass, but now we also have the gravity, and well, the node type is the same as before. We can have 1 for the nodes located in the spring, and a 0 for the nodes located on the wall. And for the input edge attributes, we have the relative position, as we often do, and now we also have the relation type, because we can have an edge between a node in the string and another node in the string, and we can have another edge for a node located on the string and a node, well, and this ball. and vice versa. So these two kind of edges are quite different, and that's why we need to encode that. So similarly, we can use a mask as we were using for the nodes, but in this case for the edges. Now the output that we obtain in each of these three cases is the velocity at the next time point. Similar as before, we cannot be obtaining the absolute location of the nodes. If we obtain the absolute location, then this will stop being translation invariant. So we obtain the velocity or the acceleration, both will be okay. In the end, we will be doing numerical integration to update the location of the nodes. During training, in their setting, they were only doing one-step prediction. They were not doing rollouts, and they trained to minimize the mean square error between the predicted velocity and the target velocity. Okay. During training, they use only one time step, and then it was quite interesting that at inference time they could produce very long time rollouts, around 1000 time steps. You have seen probably with Professor Tugay that one way of obtaining this very good long-term stability is by doing training with rollouts, by backpropagating during training through several evaluations of the model. But that can be very expensive, especially graph neural networks are known to be models not as fast as CNNs or MLPs. So although this problem is relatively simple, they only did one-step prediction, and to enhance the stability, what they did is add some noise to the input. So we have the input location of the nodes, which in the end is used to compute the relative position and also their velocity. So what they do is add some noise to this input. So during training, what we are doing, instead of learning to map the input to some outputs, we are learning to map the surroundings of a point to certain output. So if at inference time we deviate a bit, and instead of having this solution, we'll have one solution here that is not physical, the model is robust and will be able to still produce the same output. So that's the idea when adding Gaussian noise with some small standard deviation sigma, and it's quite common in these deep learning applications. Is everything clear? Okay, they only use one message passing layer. In this case, they use 4 hidden layers for the edge update function with 150 neurons, and then for the node update function, they use only one hidden layer with 100 neurons, and the output has 2 neurons, which correspond to the x component of the velocity and the y component of the velocity. Okay, so now we have our model and we train it, it's working. With which baselines should we compare it? We could consider CNNs, as I mentioned in previous lecture. We could use, for instance, a UNet or a ResNet. However, here we are only using one message passing layer. If we are using a UNet or a ResNet, we will need to have many layers. Some of them will need to learn to understand that we have different kinds of objects, and others will have to learn the physics. So it's a much more complex model, whereas here with just one message passing layer, we can learn very well the physics and have a model that generalizes very well. The other alternative is using an MLP. One of the problems with using MLPs is that they constrain the number of inputs. So if we train our model for the n-body problem where n is equal to 3, so we have 3 planets or 3 bodies, and we have this kind of input vector where we have, let's say, the location of the node, the velocity, and the mass, and the same for the other node and the other node. If we have an extra node at inference time, because instead of having 3 we have 4 or 5 or whatever, this MLP will not work because it only can handle a fixed number of inputs. We will need to train another model. So graph neural networks with message passing are much more general in these terms. Another advantage of message passing compared to MLP is the permutation invariance. So going back to this example, Here we decided to stack first the features for the node number 0, then for the node 1, and then for the node 2. But we could follow another order. We could stack first the features for node 1, then 2, and then for node 0. And similarly, we could follow the order 2, 0, 1. This is quite arbitrary, and the nodes can interchange positions while the simulation is taking place. So the model with for each of these inputs, the MLP will be producing different outputs, because if the inputs are different, then the outputs also have to be different. During training, it will learn to approximately be invariant. This kind of invariance is called permutation invariance. But we are making it more complex to the network, because it has to learn that the order of the features doesn't matter. And we have a very large system, like we will see later. We have thousands or tens of thousands of nodes. Then learning this permutation invariance becomes much more complex or not feasible. If we use instead message passing and a graph neural network, because we have that aggregation function, which is permutation invariant, it doesn't matter how we order our nodes. It doesn't matter which index we use. The outputs are always going to be the same. The other benefit of using message passing is translation invariance. So if we use an MLP, we need to inform about the location of the nodes by adding here their location. Whereas if we use a graph representation, we have the edges that are providing the relative position. So that's another advantage. And all of these things combined justify the better performance of message passing with GraphNets. I'm including this note here because a colleague last year asked me about this. So instead of having the aggregation operation in message passing, we could consider that we have a fixed number of nodes. We are okay with that. And we stack their features, well, the features of the nodes and the features of the edges into one single vector, and then evaluate an MLP and obtain the message or directly the features for the node. However, this can be translation invariant, because here we have the features of the edges which can have relative positions. This is not permutation invariance still, because here we can change the order between these features. That's why it's important to first compute the messages and then aggregate them using summation or mean. So okay, let's see if those things that we have seen that are theoretically so good for message passing compared with MLPs translate into better results, and they actually do. So here we have the 3 different experiments they consider, and here we have the mean square error with their GraphNet, and here the mean square error for the MLP. So there is a huge difference. And at the same time this paper was published, there was a similar paper being published titled A Compositional Object-Based Approach for Learning Physical Dynamics. Here the compositional approach means to decomposing our problem into objects and modeling their interactions using edges instead of using a CNN. Yeah, it's quite interesting that they applied even to a same kind of problem like these balls bouncing in a box, and was pointing out that GNNs and message passing were going to be quite important for physics-based simulations using deep learning. I already went through this note. It's about improving the stability by adding nodes to the inputs. Any question before I continue? Okay. So this next paper is also by DeepMind. They are going to use the same tools that we have seen about message passing, translation invariance, adding noise to the inputs, but they are going to apply it to much larger systems, so they will need to scale the model. And yeah, during training they have around 1,000 nodes, and then at inference time they have 10,000 nodes. So they're taking to the extreme the advantage that we saw before. We can train with a small number of nodes and then do inference with a much larger number of nodes, because if the physics are the same, the model should still scale. It doesn't matter the number of inputs. that we have. They consider different kind of materials. So, for instance, fluid, sand, goop. Goop is a fluid with a very high viscosity. I think we can see the simulation here. Why is not? Strange. Yeah, okay, we cannot see it, but they had different kind of materials, like fluids and goop, and they had to use a much larger model. So before their graph neural network had only one message passing layer, now we have 10 message passing layers. Okay, now let's see how they created the graph. So let's say we are working with fluid, so we have our fluid discretized into some moving particles like we could see here. So we need to create some edges. In the previous paper we were seeing each node was connected to every other node. That would be quite expensive if we want to use message passing because the number of nodes, the number of edges would be the number of nodes. Well, it scales quadratically with the number of nodes. We will have this number of edges. And if you remember, message passing scales linearly with the number of edges. And with so many edges, it will take ages for the model to train and also will be quite slow at inference. So we use a local connectivity. For that, for each node, we create a sphere with a radius r. This value is a hyperparameter of the model that we will need to test when testing the model. And we create edges going from each node inside this sphere to the central node. And we do that for every node. Then as features they provide the velocity at the last 5 time points and the material type. So why providing the velocity at the last 5 time points instead of only one? In theory it should be enough with only one because this problem is, we could say, deterministic. If we know the state at a point, we could know the state at the next time point. But well, because it's considerably more complex than before, we can see in practice that if we have a longer past history, the results can be a bit better. They actually tested that and saw that if we have more than 5, it stops improving, but 5 is a good value. So they decided to use 5. And for the material type, now we don't only have 2 types of nodes. Now we have 4 types of nodes that can interact with each other. We have water, sand, goop, and boundary nodes, the ones discretized in the walls. So we use what is called a one-hot vector. So this is a vector with 4 elements, and it's going to be 0 everywhere except for the material that we want to represent. So if we want to indicate that a node is of type sand, then we will have 0 everywhere except for that second node. And we have this for every node in the graph. This can also be seen as having 4 different masks, one mask for indicating if we have water, sand, goop, or boundary. Then for the edges that we just have created, the inputs that we have are the relative position, and we can also provide the magnitude of this relative position. This is the distance, but in practice this is not improving much the accuracy because we are already informing about this with this relative position. And now the output of the model, after evaluating the graph neural network, we'll see later how this graph neural network looks like, but the output is the acceleration of each node. We could also be computing the velocity. Maybe that's something that you can check for your particular problem. What's better, to predict directly the velocity or the acceleration? With this acceleration, we can time integrate once to obtain the velocity. Here they use forward Euler, but that really doesn't matter. And then we time integrate again with that velocity to obtain the location of the nodes. Here they use backward Euler, but yeah, as I said, that is not that relevant. Okay, this slide goes through the architecture that they are using. This architecture is quite popular, and still many new papers using graph neural networks continuing using this architecture, so I think it's important to have a look to it. So we have some sequential message passing layers, but before that we have an encoder for the node features and an encoder for the edge features. These encoders are just increasing the dimensionality or the number of features that we have for each node. It can be a linear layer or an MLP. So in this case, if we consider these inputs, we have the velocity at the previous 5 time points and the material type. So let's say we have 19 inputs, and we increase the dimensionality to have 128 features for each node. Similar for the edge features, we had 4 features if we are in 3D, and we use a linear layer or MLP to go to 128 features. And this latent dimension of 128 is kept fixed in all the intermediate representations. So that's what they call the encoder. Then we have what they call the propagator, which is just several of these message passing layers. They use a message passing layer with edge update function and node update function, both modeled with MLPs. They use a small or relatively small MLPs with only 2 hidden layers. In this case, the depth is provided by the number of message passing layers, not by the size of MLPs. We'll see later that the number of message passing layers is a very important hyperparameter, much more than the depth of these MLPs. Yes? Mhm. Yeah. Mhm. Well, the outputs are obtained for each node, not for the edges. So we, based on the current location of the nodes, we create edges. Then we have, well, the inputs, which is the velocity of the nodes and so on. We evaluate the network and we obtain the acceleration. So at each node, we obtain the acceleration. Yes, and after, yeah, not for each edge. And after we have this acceleration, we can time integrate to obtain the velocity. So this velocity will replace the previous velocity that we had as input for the next time we evaluate the model. And we also update the location of the nodes. So after we have updated the location of the nodes, we will need to create new edges because their location has changed. So nodes that were close before, now they can be far away, so we don't need any edge. Mhm. Yeah, yeah. So yeah, well, we had here maybe I will go back to it later. Here we have the encoders for the node and the edge features, then several message passing layers, and then we have the decoder. In this case, we only want output for the edges, not for the nodes. So that's why we don't have a decoder here for the edges. These edge features will not be used. And here at the end, we have 128 features for each node because it was the latent dimensionality. And we use this decoder, which is a linear layer or an MLP, to decrease the number of features. So we go from 128 in this case to 3 if we are in 3D, the 3 components of the acceleration. Okay, we have here what this video wants to work now. So we have here some example when they are simulating a fluid. So they train here with 2,500 particles, and then at inference they have 28,000 particles. And we have the prediction and the ground truth. We see that the resemblance between both is very high. Also, the domain is larger than when they use during training, and the rollouts are very long. This was the inference domain or test domain, and here we have the training domain, which was smaller and had a smaller number of nodes. So that's quite advantageous for this kind of SPH or Lagrangian-based simulation, training with small systems and then extrapolating to larger ones. And well, the part of the success here is again similar as before. We are using message passing with translation invariance, permutation invariance, and we are adding noise to the inputs in the similar way as we were doing before to enhance the long-term stability. Here we have some simulation where we have different kind. Well, here they only consider one kind of material, but here we have three kind of materials. This is also some generalization cases. The graph neural network works the same. If we have 1, 2, 3, 4, or any number of materials, we just need to be using those hot vectors for indicating the kind of material that we have. And well, here also they use a relatively small number of nodes for training, 1000, and then at inference time they use 4000. They use 4000 nodes. Here are some examples of how these different kind of materials interact. Okay, and here in this slide we have a summary of different ablations and different hyperparameters to take account into the network. So let's first have a look to the last column. In the first row we have the one-step error, and in the second row we have the mean square error through the whole rollout. This first row is not very relevant. Normally we are interested in the accuracy of the simulation through the whole rollout, not just at the next time point. And we can see here in this last column the importance of using relative positions, which is the same as saying having a translation invariant model. So we can see that for the rollout, if we have a translation invariant input, the error is half of what we would have if we are not considering this invariance. Other thing to have a look at is the noise. So here they are adding noise with some standard deviation to the input. The intensity or the value of this in standard deviation increases to the right. And we see that if we only consider one-step predictions, then apparently adding noise to the inputs during training is not good because the error increases. But as I said, we have to look to the whole rollout, and we see there is an optimal value here for how much noise we should be adding. So for this, we just have to do this test and pick the value that is the best one. There's no other option. In this other column, we have the option or the alternative of sharing the weights between the message passing layers. So in this GNN that we have, these message passing layers are all the same, but they can be sharing the weights or having different weights that have to be learned independently. The option nowadays, we know clearly that is having different weights, but since this was the first model considering this, they are showing here the results, and we see that there is some improvement when using individual weights for each of the layers. And I have left these two columns for the end because they are probably the most important ones and both are related. So we have here first the influence of the number of message passing layers. So we see that as we increase the number of message passing layers, the error is decreasing, which makes sense. The explanation for this is partly because we are increasing the size of the receptive field. So when we have more message passing layers, each node can see what's happening on nodes located farther away. Whereas if we have a small number of message passing layers, then each node can only see what's happening to very nearly nodes, but not what's happening far away. And if we have incompressible fluids or other kind of physics where we have a non-local behavior, then it's important to allow the information to travel fast from one point to another. And here the connectivity radius is also related with the same. This is the radius r of the sphere that we are using for creating the edges. If we have a larger radius, we have a larger receptive field, and also the error is decreasing. Yeah. Mhm. You mean fixed times? The size of the time step. Yeah, okay. Yeah, the size of the time step size is keep fixed. So in numerical simulations, we need a very small time step to guarantee numerical stability. Here we can use a larger time step because we don't have those problems. If you use a very large time step, then we are going to get very bad results, but it's also going to be faster. So for that, the only option is to pick some of those time step sizes and see which one in the end is better at the end of the simulation with which one you have highest accuracy. Mm, no, like no, we don't use that much. So there were some papers having a look to using Runge-Kutta and other kind of time integrations where you learn the derivative instead of learning directly the result, and then you can use different time step sizes or if, even different integration schemes. But it's not something that has become popular. We normally use a fixed time step and just Euler integration. Okay, so that was all regarding that paper. We can have a short break now. Well, one question before. Mhm. Sorry, the mhm. That depends a lot of the kind of application. So there are some applications more focused on engineering cases, like what we will see next day, for instance, these CFD simulations. In this case, if we use the same hardware, like CPU or GPU for both solvers, the speedup can be around 100 times faster using a GNN. But for more things related with computer graphics and wanted good physical, good visual simulations like here, which doesn't have to be numerically accurate, just have to look good. The the existing software for doing this kind of simulations is already quite fast because it has lots of assumptions. So the speed up is not that much. It's more or less at the same level or one order of magnitude faster. Yeah. Any the other question? Well, for one step prediction, the error is always very small because the particles haven't moved much. Then after the rollouts, particles can follow. Yeah, in this case, for instance, 10,000, sorry, 2,000 time steps. So at the end, the locations are quite different. Okay, so we can have now a 5 minutes break, and afterwards we can have a look to some short code to see more in practice how these things are implemented. Okay, let's continue with the lecture. Can you see properly, or do you want it bigger? Okay. So this goes through how to use in PyTorch Geometric, which is a package for Python and specifically for working with PyTorch and graphs and graph neural networks. And I think it will be useful also for the exercise that you will be doing. So PyTorch Geometric provides this class called data, which is going to use to represent the inputs and the targets of our graph. The attributes that we normally have include the position. This can have any name, but the convention for this is to use the position, and the same for the input features at the nodes we use X, and for the target features at the nodes we use Y. So here this position vector is going to have 4 rows and 2 columns, so we have 4 nodes and 2 spatial coordinates, the X and Y coordinates. Then we have the edge index, which is the equivalent to the edge list that we saw at the beginning of the previous lecture, but it's the transpose of it. So here 0, 1 is an edge going from node 0 to node 1. We also have edges 0, 2, 2, 3, and so on. So you can see that in the first row we have the sender nodes, and in the second one we have the receiver nodes for each of the edges. Then we can assign some input features for the nodes. And since we had 4 nodes, or we decided that we have 4 nodes when we created the position here, we are assigning 4 feature vectors to our graph, and each of these feature vectors has 2 components. We have 2 input features per graph. And then we have the edge attributes, which are the input features for the edges. We could provide something random like we are doing here for the node features, and we can also do what we have been seeing that we normally do, is use the relative positions between the sender node and the receiver node. So with this we are getting the indices of the sender nodes, is these nodes here, and we are getting their position. And then we are doing the same for the, this is for the receiver nodes, and we are doing the same for the sender nodes. We get their indices, and then we get their locations. So with this we are going to obtain the relative position. This is a matrix with number of rows equal to the number of edges, which was 5, and the number of columns is 2, because we had 2 coordinates for each node here. And we can plot this graph just using pyplot. So we see that, well, this is what we have. We see that we have 5 edges, 1, 2, 3, and here we have a bidirected edge, so 4 and 5. And PyTorch Geometric provides some methods for this graph. For instance, we can check the number of nodes doing this, the number of edges, the name of the features that we are using, the number of node features, and we can check other things like if we have isolated nodes or if we have self loops. For this they have their documentation, which is quite good, so if you want something in particular you can have a check. And another very useful thing that they provide, in my opinion, I think is the most useful, because other things you can code it yourself, but this could take some time, is the option of creating batches. So to create batches, they provide batches of graphs. They provide this class called batch. Let's see how to use it. So we have our graph that we had before. We create a copy, name it graph1. Do the same to have graph2. And to make them different, we are going to shift the location of the nodes in the graph2. We shift it by 3 units on the x direction, and then we can create a batch with this. So I also mentioned this at the beginning of the last lecture. When we create batches with graphs, we don't create an extra dimension like we do with CNNs, where we stack them like that. Instead, we are going to sequentially change the indices for the nodes. It's like we have a large graph where we have 2 disconnected subgraphs. For instance, if we now check the number of nodes that we have in our batch or in our larger graph, we see that we have 8 nodes. Before we had 4, and we had 10 edges. In this case, we have the same number. Each of these subgraphs has the same number of nodes and same number of edges, and actually the connectivity is the same. But of course, they can be very different graphs. That's why this is useful. And we can plot it like before, and we see that effectively we have a large graph consisting of two subgraphs. Also, when creating batches like this, we have this new attribute, which is generated by PyTorch geometric, which is indicating to which graph belongs each of the nodes in the batch. So, for instance, if we print it, we see that the first 4 nodes belong to the graph 0, and the last 4 nodes belong to the node 1. And we can plot it. We see that this is the first graph, and this is the second graph. Okay, now let's have a look to how we could implement message passing, or one kind of message passing. Here we have the message passing, our user-defined message passing class. And this we do it like in normal PyTorch. We are inheriting from Torch module, and we are creating the edge update function, which is a small MLP, and the node update function, which is another small MLP. Now in the forward, just to be a bit organized, we get first the indices of the sender nodes and the indices of the receiver nodes. These were stored in the edge index, if you remember, which is the transpose of our edge list. And we apply the edge update function. So for that, what we were doing is taking the features of the edges and concatenating it with the features of the receiver node and the features of the sender node. So we have a larger vector now, and we apply this MLP. In this MLP, we have a batch dimension that corresponds in this case to the number of edges. It's not the same as the batch dimension when training MLPs in an isolated way, and the other dimension is the features of the edges. Then we have this aggregation, for which we use the scatter function. PyTorch geometric provides its own scatter function. Also now, normal PyTorch also includes it. And we are specifying that the aggregation is summation. We could also have a mean aggregation. And maybe you are not that familiar with the scatter function, that's why I included this diagram here. What we are passing here the receiver index means that we are going to be aggregating, taking into account which is the receiver node. So here we have, let's say, the one of the features for all the nodes. This node had, for each of the edges, this edge had as receiver node 0. This one also had node 0, and this also had node 0. So these features have to go together to the addition or min function, and it happens the same with the other edges. We aggregate them based on which was the receiver index. And once we have that aggregation, we concatenate it with the features of the nodes. We have the concatenation and apply the node update function. So that's it for the message passing. We could then have the node encoder and the edge encoder, like what we saw before for the previous paper, where we are just increasing the dimensionality. We are going from 2 input features to the inner dimensionality or latent dimensionality. And the same for the edge features, and then we will just have to apply message passing layers. Here I only had one message passing layer, but we could have several message passing layers, and then we apply them here. So we get as outputs the updated node features and the updated edge features. So then we could keep iteratively applying different message passing layers. Well, here we will need to do GraphX to take it into account. To the next time use the updated values, but well, you get the idea. Okay, and we can apply that neural network to the graph that we had before. And we can also apply it to the batch, and we don't have to the batch that we created before by joining two subgraphs. And we don't have to do any modification to the graph neural network. That's why we create batches that way. Okay, to finalize this, I have another example here. Python Geometric also provides some datasets. This is a dataset related with RANS simulation, which are some kind of steady simulations of fluids. And you can download the dataset like this and load one of the graphs like this. If you are working with some data that you are not familiar with, let's say when you are in your job position, I recommend you to print the graph to see what you have. So you see that you have these input features. So this is probably the number of nodes in the graph. These are the number of input features. The same for output features, the location of the nodes. You could already use this to visualize what geometry you have. And we see that we don't have edge index or edge attributes, so we will need to create those edges. As I said before, we have the location of the nodes, so we can use scatter function for pyplot to plot what we have, and we can plot each of the input features. We had 5 input features, and well, here is a bit difficult to tell what we have, but you just check the documentation in this case. For instance, here we have the distance to the wall, and the same, we could do the same with the targets, which in this case were the horizontal component of the velocity, the vertical component, the pressure, and the turbulent kinetic energy. And in this case, the graph that we had in this data set didn't have edges. We printed the graph and saw that we didn't have edge attributes or the edge list. So we will need to create some transformation to do this. And these transformations are common for other things, not just for creating edges. For instance, here this mesh is very fine. We had more than 100,000 nodes. So we will need some transformation to drop some nodes. In this case, we are randomly dropping some of the nodes. And we have another transformation for creating edges. Here the edges are creating using the k nearest neighbors. So for each node we send an edge from its k nearest nodes, which for that k I'm using number of 6 here. And then for the input features, for the attributes, I'm doing like we were doing before at the beginning. We use the relative position. And both these transformations are passed to this transforms.compose, which is just from standard PyTorch. Maybe you have used it already before. And these transformations are passed here to the dataset when we create it. So now if we visualize it, we see that we have a smaller number of nodes. We were keeping only at 10% of the nodes, so we have only 17,000. And now also we have edges here, and you can check that the number of edges will be this number of nodes multiplied by 6, because we were creating 6 edges per node. Okay, so that's all related with this. I hope it was illustrative. Okay, so now let's continue with another paper. In this case, yes. Yes, I uploaded last week. It's not in the section for the current week. It's in the section for the previous week. Okay, so yeah, before we were looking into a very general form of message passing. It was quite powerful and expressive because we were using MLPs, multi-layer perceptrons, for the node and for the edge update functions. Now we are going to have a look to a simpler form of message passing, which is linear instead of being non-linear, but it's also going to be faster and is based in some of our knowledge of physics, so it's also going to perform quite well. So the idea here is based on the discrete convolutions that we have in CNNs. In CNNs, if we want to obtain the convolution with a filter J at a location X, what we do is we multiply the features at some neighboring pixels with the value for the kernel at that location, and we add those results. If instead we had continuous signal and a continuous filter, instead of doing the summation, we could do the integral. And when we work with graphs, actually we could have something similar to this, because the nodes have an unstructured location in space. They are not in a regular grid like what we have here. So that was the motivation of this paper, using something similar to this idea of continuous convolution. But although the nodes can be anywhere in space, they are discrete. We don't have a value for every location in space. So what they are going to do is have a continuous, have a continuous kernel, but have still a discrete signal. And the kernel that they have, the continuous kernel, is this one, which has a compact size. We can see this more clearly here. So this is this expression for message passing, for updating the features, updating the feature f at the node j. So what we have is the feature of the neighboring node. So let's say we have this central node, which is whose features we want to update. We create, first we create a sphere or a circle of radius r. So we have some edges going from, we have an edge going from each node to the central node j. And in our convolution, we have first the features of this. We have first the feature of this sender node, and then we multiply with the kernel. This kernel is continuous and is compact, which means that it has a value everywhere inside this circle or sphere if we are in 3D. But we cannot evaluate it straight away. What we do is, with this relative position, which is this one here, we transform it to another system of coordinates. We are transforming this circular domain, which we have here, into a square domain, because here we can store the location of the nodes in a regular grid like we commonly do with CNNs. The transformation function is here, but you don't need to worry about this. Also, if we are transforming a sphere in 3D into a cube, it's more complex, but that's not the relevant thing about this. Okay, so once we have transformed our node from here into somewhere in this new domain, we can get the value for the kernel there. We are only storing the values at discrete locations, and if we want to get the value at this intermediate location, we just do bilinear interpolation. So that way, every point here in this circle is assigned with some value for the kernel. What we are doing is transforming the square into a circle, and we have continuous values because inside this square we can we do bilinear interpolation for the weights. And here, this last bit here is not strictly necessary for this to work, but it helps to improve the accuracy. This is a window function that looks like this bell that we have represented here, with a value of 1 when we are here and a value of 0 when we go outside of this circular domain. So this is done to make it clear that nodes close to the central node should have a higher weight than nodes located farther away. If we don't use this function, which is called window function, then the model will learn it during training, but we have to, or the model has to spend some effort and weights, and it could complicate convergence in learning that. So it was actually better to use this window function. And this window function is also quite common in SPH, in smooth particle hydrodynamics. We see them when we want to interpolate features based on surrounding nodes. Before I continue, do you have any question about this slide? Okay. Okay, so that was for convolving one kernel with some signal, but we in practice we have multiple input channels and multiple output channels. So this would be, instead of a single value, a feature vector, and here this G will store C in times C out multiple channels. When we evaluate with our three-dimensional or two-dimensional vector, we get a matrix. And this expression here, of course, still falls within the definition of message passing. This is the message, this is the aggregation, and then we have the node update here. The hyperparameters that we have is the number of input channels, number of output channels as usual, and then the size of the receptive field, which is this radius r for creating the edges and defining the window function. And we also have the kernel resolution. So this corresponds to the number of weights that we are using here. In standard CNNs, in discrete convolutions, if we have more weights, it's because we have a larger receptive field. In this case, if we have more weights, we are not increasing the receptive field. We are just increasing the resolution of these kernels. So if we have features that spatially vary a lot, then we will need to use more weights. If they don't vary that much, we could still use a smaller number of weights. And as you may notice here, this message passing function is linear. We don't have any activation function. So every time after we apply this message passing layer, we need to apply an activation function. Okay. In this paper, they only consider fluid simulations like what we have here, similar to the one we saw before. And they consider two types of nodes, fluid nodes and wall type nodes. And in this case, they work with an heterogeneous graph, meaning that each of these nodes has different kind of input features. The fluid type nodes have as input their velocity and also their viscosity. We can have different viscosities. And this one here is a bit weird. They are just adding it because they don't have bias term in their message passing layer. So this is a way of including the bias, but probably it's not the most elegant way. And for the wall type nodes, they are providing as input the normal vector pointing to us inside the domain. And although they have different kind of nodes with different kind of input features, we will see later when we look into the architecture that this is not a problem, can be solved easily with message passing. And they are not using edge attributes. Normally we use the relative position between the nodes, but we are already taking this into account when we evaluate our kernel. Okay. In the previous paper, we were directly getting the acceleration for the nodes after evaluating the model. Here in this paper and the one that we will see afterwards, they split the problem into two subproblems. First, they time integrate the external forces, and then they use the graph neural network to take into account the interactions. So these, well, external forces, we don't have really external forces. We only have the gravity. So this acceleration will be the acceleration due to gravity, and we can time integrate once to obtain the velocity and then again to obtain the location of the nodes. But this was ignoring the interaction between the particles, no, that can collide with each other. So that is where the graph neural network comes into play. We feed as input these velocities and use these positions to evaluate the kernel. And the graph neural network is going to provide some correction to these intermediate velocities. So after we evaluate the network and we obtain that correction, we just have to add it to that intermediate location to get now the correct location for the nodes, accounting for the external forces and also the interaction between the nodes. And we can also correct the velocity based on the value that we got for the location of the nodes. Here again, once again, see that we are obtaining as output some correction for the coordinates of the nodes, but not directly the absolute coordinates of the nodes, because that would not be translation invariant. This is just a difference into the location, so it's still translation invariant. Okay, and here we have the architecture, which looks a bit complex to understand in this diagram, but I will go through it. So remember that we had different kind of nodes. So we have these nodes for discretizing the wall and some nodes for discretizing the fluid. So in the first layer of the model, they are going to apply their message passing layer, which they call continuous convolution, by taking into account for each node only the wall type nodes. So this node will have 3 or 4 neighboring wall type nodes that are sending a message to it. Other nodes located inside the fluid will not have any wall type node, so the output will be equal to 0. Then message passing is applied also, but only with the fluid type particles. So in this case, if within the sphere we have any wall type node, we ignore it. So with this we obtain 32 features and 32 features. That depends of which hyperparameters you choose. And because in the message passing they were not directly taking into account the features of the central node, they had to add this skip connection. That's what they are representing here. This is a weighted skip connection. And they are adding the result from the convolution with fluid particles and the weighted skip connection, also applying the activation function. And then to that, they concatenate the result that they obtain for the wall type nodes. So everything, it looks a bit complex, but well, it's not that complex. And then the next layers are just applied considering the fluid type nodes. We already informed about the wall type nodes in the first layer, and at the end we obtain the correction for that intermediate location for every node. Here we have their loss function. I think here it's interesting to have a look to some things. They don't use the mean square error. Instead, they use some coefficient gamma with a value of 0.5. They provide an explanation for that, but I think it's more based on empirical results than in some physical evidence or physical justification. What I think is interesting though is using this weight. So after they compute the error for each of the nodes, they are going to give a higher importance to some of the nodes. Based on this, they give a higher importance to the nodes that have a small number of neighbors. Why so? Well, if we have a look to, for instance, this simulation, you may see that this node here has a very small number of nodes. Also, these ones here have a very small number of nodes. And if we want the simulation to look visually good for computer graphics, then these are the nodes that are going to be easier to tell if they are grown or not for some user or for the audience. That's why for these nodes that have a smaller number of neighbors, they are given higher importance in their loss function. And for training, they train by with a rollout, so they evaluate the model twice and then do backpropagation through the 2 evaluations of the model. The things that you saw in the first part of the course with Professor Tugay still apply with graph neural networks or with any architecture in reality. Okay, so yeah, here they have some ablations showing how the model performs when they remove some of their contributions. Like for instance, we can see if we remove the window function, the error at the last time step is larger than in their own implementation. And same as before, we can train with a small number of nodes and then go to other extrapolation cases where we have a larger number of nodes. Okay, um, that was the main contribution of the paper, but they also had a look into inverse physics. I think also in the first part of the course you were talking about the inverse problem. In this case, they consider something relatively simple, but we will see later how this simple idea can be applied to a more real, complex, and realistic case. So in this inverse problem, we know the evolution of the fluid, but we don't know the viscosity. So if we know the evolution of the fluid, we know the location at one time point and the location at the next time point, then we can compute, given the first time point, the intermediate location for the nodes, and given that intermediate position and the final position, we can compute the correction delta x that the network should be predicting if we knew the viscosity. Now we can evaluate our network. The network was trained before, now we fix the weights, and we evaluate the network with a random viscosity value because we don't know the value. This viscosity will go into the input features for the nodes, and we evaluate the network and get some delta x. This delta x is not the one that we were observing, it's not the one that we know from the given simulation. So we can compute the difference between the correction predicted by the GNN and the correction that we got from the data, the one that we were observing. And we have this loss function, which in this case is the absolute error, but we could also use the mean square errors or the L2 norm. And we can backpropagate now to compute the gradients of this loss function with respect to the viscosity. So this is like the same way that when we train the network to optimize the weight, but now we don't want to optimize the weights of the network. What we want to do is minimize this difference. We want the prediction to match the observed result, and when we do so, we will be getting closer and closer to the value for the viscosity. So here we update with some learning rate, and now that our viscosity is updated, we can again go to our model again, compute the loss function, get the gradients by backpropagation with automatic differentiation, and update again the value for the viscosity. Is this clear? Okay. So these simple ideas were also used in more realistic cases by another paper by DeepMind called Inverse Design. They are using the same graph neural networks that we saw before the break, where they have some sequential message passing layers with MLPs for the node and the edge update functions. But the focus of this work was not in simulation or in the neural network. That one is already given. What they want to do is some optimization. So let's have a look to these videos. So in this case, we have some fluid going out of a pipe. We have some surface, the balls collide with the surface, and in the end, they hit the floor. And the objective in this case is that the balls, well, the fluid, when it hits the floor, its velocity should be pointing in the direction given by this pink line. So that's the condition that they establish. In this other different case, the condition is that the balls have to go inside this purple area. So if we consider how these simulations are done, this is done as before. We have some nodes for the fluid, we have other nodes for this green surface. Also, we haven't seen how to work with inlet boundaries, but here we are just creating nodes. So we fix a flow, some flow rate, and we are creating nodes at that specified flow rate. That's how we simulate the inlet. And this GNN is able to simulate these balls going down due to gravity and colliding with this surface, because we can work with different kind of materials and we can time step. Okay, so now how we get the geometry or the shape for this green surface that ensures that we are meeting our objective. This green surface here has a its projection to the floor is a square, so it's this square here, and they initialize the values to be random, so something quite chaotic, like you can see here. And we are going to run the simulation for k steps. We run it for k steps because if you notice at the beginning there's not much going on. We have to wait for the simulation to converge. We have to wait for the simulation to converge. We run it for some steps, and now is when we check if the direction of the fluid agrees with the direction of the green line, or we check if the balls are going, if the fluid is going inside the purple area. So yeah, we have run our simulation for for some time steps. Now we evaluate the loss function. In this case, it's quite simple to come up with a loss function. We could, for instance, compute the mean square error between this direction and the direction of the velocity of the particles. And now the learnable parameters, once again, are not the weights of the model, but the height of the nodes in the green surface. And when we do backpropagation now, we are doing backpropagation to compute the derivative of the loss of our condition with respect to the height of the nodes in the green surface. This is a bit more, well, it's quite expensive computationally because we need to backpropagate not just through one evaluation of the model, but through k evaluations of the model. What's the advantage, however? Well, we do this iteratively, so after we get those gradients for the height of the nodes in the green surface, we update the value of the height, run the simulation again for some k steps, then update the value again. With this method, the gradients that we are getting, well, the gradients for the loss with respect to the height of the nodes are quite accurate because we are computing them by backpropagating through our physical model. With other approaches, like with traditional gradient descent optimization, where we just run the simulation once again and assume the gradients to be linear, those gradients are not accurate. So when we try to convert to the optimal solution, we are oscillating a lot, and we will need to use a small learning rate or update step. Whereas here the gradients are quite exact. But so that's an advantage. The optimization is going to be faster. We need a small number of optimization steps, but each of these steps is quite expensive because we need to backpropagate through several evaluations of the model. Okay, is this clear? Okay. So now we can begin having a look to the last topic for today. I'm not sure if we will have enough time to finish, but let's begin. So we have seen already the advantages of having translation invariance and permutation invariance in our message passing layers. And now we are going to have a look to another physical principle that would be interesting to respect, which is the conservation of the total linear momentum of the system. This is also a paper by our group, and we are going to be looking only to SPH simulations, Lagrangian simulations of fluids. And we need to review some physics to understand how are we going to guarantee the conservation of momentum. So we have a discrete system of particles, our fluid particles, and each of these fluid particles, I, has this linear momentum. If we want to obtain the total linear momentum of the system, then we just compute the summation across all the fluid particles. This, well, the linear momentum of each of the particles, this one here, can be modified by forces. The forces can be external or internal. I denote external forces like this. So this is external force acting on node I during a infinitesimal small delta t, which is causing an infinitesimal change in the linear momentum. And we also have forces between other neighboring particles, no? They can interact with each other, so these are the internal forces. And this denotes the force due to particle J into node I. Okay, and we know that based on Newton's third law, which is also known as the action-reaction principle, the force of particle J into node I is the same as the force from particle I to node J, but with a minus sign, so in opposite direction. This means that when we compute here the summation across all the particles to obtain the total change in the linear momentum of the system, because this summation, because we will have here this summation, these forces will cancel each other because of this, and the total summation is going to be equal to 0. So that's what I explained here. The total change of linear momentum, it's only due to external forces, because the internal forces are going to cancel each other because of the action-reaction principle. So if we manage to embed this symmetry, the action-reaction principle, into our message passing layer, then we are going to be ensuring that the linear momentum of the system is preserved. We just need to see how can we guarantee that we are respecting this, the action-reaction principle. So as in the previous paper from our group, we are decomposing the problem into first considering only external forces and then considering internal forces, and that's actually necessary for this method to work. So we consider, well, this is the same as we had before. So we have the external, well, the acceleration due to external forces, which is only the gravity. So we get an intermediate velocity and an intermediate location for the nodes, which is not the correct one. It's some prediction that is ignoring the interaction between the particles. And then given this velocity and this location as inputs to our GNN, not the absolute locations, but the relative location for evaluating message passing, we get the correction. We get how to correct the location of the nodes. And so this part here is only taking into account external forces. External forces can change the linear momentum based on what we have seen here. Is the internal forces, the ones modeled by the graph neural network, the ones that shouldn't change the linear momentum, and so the graph neural network must ensure that we are conserving or respecting the action-reaction principle. Okay, how to do so? Well, this is the output that we obtain at the last message passing layer, and we can again go back to considering the action-reaction principle, which is saying the force from node J to node I is the same as force from node I to node J, but with opposite sign. We can write this as the mass times the acceleration, and because the mass for every fluid particle in the simulation is the same, they cancel out the same as the time. So we get that what needs to be with same absolute value and opposite direction is this change in the position of the nodes, which can be understood as the change in the location of node I due to the existence of node J, and vice versa. And this is the output that we were obtaining from the network. It's not exactly the same, because here we have the result of taking into account all the nodes, not just this node J, but it's something similar. And where does that appear? Well, it appears in our last message passing layer. So if we have this output of the network, the correction for the location of the nodes, and we decompose it as the contribution from the different nodes I in the system. In the last message passing layer, we don't take into account all the nodes. We only take into account the neighboring nodes of this node J. So instead of considering the whole system, we only consider the neighbors. And we can see now here that this is a message passing formulation, where this is the summation or aggregation, and this is the message. So we need this message, or we need the message from node I to node J to be the same as the message from J to I, but with opposite sign, is what we have here. And we call this anti-symmetric because, well, we are evaluating them with the same vector but with an opposite sign, and we should get also the result that we get should also be opposite. So, well, that's the definition of antisymmetric. And you can clearly see here that the messages that we were computing with our continuous convolutions, of course the message that we are computing using an MLP don't satisfy this equality, and it would be too complex to ensure that. But if we have something more interpretable, like in our continuous convolution, we can have a look and see if that's verified. But we see that no way, because although this term here is symmetric, if we have here xj minus xi, the result is going to be the same because it's a radial function. Here we already have one difference. We have the features from the sender node instead, and we cannot have at the same time the features for I and for j. And also this thing here is going to be returning a different value if instead of xi minus xj we have xj minus xi. So we can take that function and modify it slightly so that the antisymmetric condition is satisfied. So now instead of just having the features of the neighboring node, we also have the features of the receiver node. So now this will be symmetric if we change j with I and I with j. This was already symmetric before. And this we can impose it to be antisymmetric by choosing an antisymmetric kernel. How do we do that? So we are going to learn only half of the kernel, and the other half of the kernel is constrained to be the antisymmetric of this thing that we learned. So we had here a 1, here we will have a -1, if we have a 2, we have a -2. So that way if we evaluate this with xj minus xi, we will get the same but with a minus sign. So now with that we are satisfying this condition, and we can apply this message passing layer at the end of the GNN, and we will be obtaining an output that approximately guarantees that we are conserving the total linear momentum of the system. Next day we will continue having a look to more contributions of this paper and some results. But before, you have any question? Okay, so I think we finished for today. See you in 2 weeks.